It's my great pleasure today to introduce Thorsten Ensslin, my former PhD supervisor. Thorsten did his PhD at the University of Bonn with Peter Biermann. After that, he moved to a little place called Toronto for half a year as a postdoc down in the physics department. After that, he moved to Munich as a postdoctoral fellow at MPA. And there, unfortunately, he got stuck in a permanent position. So he is still there. When Thorsten was here, he called himself a radio astronomer. After that, he worked on cosmic rays, galaxies, then moved more into cosmology. And these days, he's leading a crusade against the poor usage of statistics in all fields of astrophysics, which led him to develop what he calls information field theory. And I think he'll tell us what that is.
Okay. Yeah, thank you. It's always nice to be back in Toronto. Also, I don't think I'm riding a crusade. I just try to convince people to use better tools. Well, some of them won't and come even to my talks. Okay, information field theory. In cosmology, we want to measure the fabric of space-time. We want to see wiggles in space-time in order to get information about the earliest moments in the history of the universe, about the inflaton, for example. And when we see certain wiggles in our data, we want to be sure that what we saw is really an indication of the inflaton and not something else. And therefore, one has to be careful when one deals with information on spatially distributed quantities on fields. The problem one is facing is that a field has an infinite number of degrees of freedom. At each location in the continuous space, the field could have a different value. However, the data which we obtain from our instrument is always finite. So a finite number of numbers should be used to determine an infinite number of field degrees of freedom. Mathematically, this is impossible, right? So we have to do something about that. We need additional information. The information we have in the data alone is not sufficient to tell us what the field is at each location in space. The information we might use in this are physical laws, like Maxwell's equation, continuity equation, hydrodynamics equation, depending on what kind of field we are interested in, symmetries, if they exist for this field, the continuity of the field. Most physical fields don't jump in their values from one point to the next, but are similar. The reason why they don't jump when you go from one point to the next is that for many of them, it costs a lot of energy to be different in different locations. If the electrical potential is different in two locations, you have electrical fields, and this squared is an energy. So continuity is very important. In cosmology, we can also use very often statistical homogeneity or isotropy of the field, at least as a starting guess for what is going on. Most important, I would argue, is that space, time, and fields are continuous. So if you know something about the field at one location, you also know something about the field in the environment of that location, up to the extent where the autocorrelation of the field decays. And so you can't use the measurement at this location in order to make predictions about other locations. But within that volume, the autocorrelation volume, the measured value is a good indicator of what is going on. And we should use that. But how can we put all these things together? So how can we combine the concrete data and the abstract knowledge into a statement about the field? And I would argue we need simply information theory for fields, or information field theory. So what a field is, I think every physicist knows. So let's talk for a second about information theory. In information theory, you try to make, you try to find out if a statement is true or false. So that's the classical domain of mathematical logic. However, in science, we never can, or we rarely can use logic directly because, as Maxwell already pointed out, the actual science of logic is conversant at present only with things either certain, impossible, or entirely doubtful, none of which, fortunately, we have to reason on. Therefore, the true logic for this world is a calculus of probabilities. So what Maxwell says, or said some time ago, is if you want to extend logic to the domain of uncertainties, then the formalism we should use is probability theory. And actually, in the middle of the last century, there was a mathematical proof that the only way to extend mathematical logic to the realm of uncertainties is represented by the probability theory we learn in school. Okay, so now we know how to put values onto statements indicating how much we believe in them, how much we think they are true. We put a 1 if we are absolutely convinced, and we put a 0 if we are absolutely convinced they are wrong, and some number in between. And in order to make all this self-consistent, we have to follow the rules of probability theory, and one is well known, is Bayes' theorem, which allows you to invert the relation between data and signal. So if you know the probability to obtain a certain data given a signal you're interested in, then you can use this Bayes' theorem in order to tell you what is the probability of the signal being of a certain being a certain way given the data. If you can make some prior assumptions about the probabilities of the signal and normalize everything properly. That's not new. It's Bayes' theorem, 250 years old, which is probably not well known is that you can write Bayes' theorem also in a different form, which is also known for more than 100 years. Namely, you can translate it into the language of thermodynamics. So I just write this numerator of this equation as e to minus a Hamiltonian, or an energy. And this energy I just define in a way that it represents this numerator. So this energy is minus logarithm of this, the joint probability of data and signal as here split into these two probabilities. So I've done nothing. I just rewrote the equation. And then this normalizing probability of the data down here, I just give it a different name, and I call it a partition function. So I just gave mathematical terms a new name. And I've mapped my inference problem onto statistical mechanics. And statistical mechanics, we know how to deal with in physics, since we are doing this for more than a century. And so our inference problem becomes a statistical field theory if it deals with fields. Since we are not asking the question, how often does the field we want to measure has this or that configuration, but we ask the question, what do we know about that field, which certainly has only one configuration, given the data we have? I don't call this statistical field theory, I call it information field theory. But the mathematical formalism is exactly the same. It's just the way we interpret these equations is different. Actually, one can go a step further and argue that thermodynamics is nothing else, or statistical mechanics is nothing else than Bayesian reasoning. But that's a different talk. A few puzzled views I see. Any question at this point? Okay.
Just one for clarification about the word information versus statistics. So information, you have only one realization of the data, not infinitely many.
I have one realization of the data, and I ask, what does it tell me about my signal? That's the field I'm interested in. And I don't know, and will probably never know, what is the correct answer for that field. So I have to describe the uncertainties about the different field configuration, and therefore I have to define a probability function over the space of field configuration. And here is a recipe how to do that. And I just use a language which is more familiar to us physicists than this expression. But they're equivalent. I could use either of them.
So does it mean anything that your new way of expressing this requires the joint probability distribution? Or something profoundly like that?
No, I can define a Hamiltonian for every probability distribution, but just for, if I want to express Bayes' theorem, then it looks exactly as this Boltzmann sum. It is actually the same, I would argue.
Just make sure it's P of D, D comma S.
This is P of D. This P of D? Here. Well, the joint probability is what is written up here. So these two, so the probability of getting first a signal in a certain way, and then the conditional probability, given the signal that the data then is this, is equivalent to the joint probability. Okay? So this Hamiltonian is basically the negative logarithm of this numerator. Okay? So now we have, in principle, the formalism. What can we do with that? Assume we have some data taken by an instrument which looked at some field. The formalism can't tell us what the field is. It just can tell us what the field could be and how likely it is. But then we can ask, okay, on average, what it is. Or what is the uncertainty? What is the spread around this average? So what we want to do is we want to calculate expectation values over the conditional probability of our field given the data, so constrained by the data, and other knowledge we put in. And in this average, we put, say, the field at this location and the field at that location if we want to calculate a 2-point or n-point correlation function. If we just put one of them in, let's take this away. If you just ask for the field at this location, then we calculate what should this field be on average given all the uncertainties I have. And then this is what an astronomer would call an image. Because for each location, then we get one expectation value, and that's our best guess how the field could be at this location. Okay, so how to calculate this? Oh, that's very simple. All we have to do is we have to average the fields at the different locations over the probability distribution of the field given the data, which we can construct via Bayes' theorem, and integrate over all different field configuration. And here comes the difficult part. This is an infinite dimensional integral. Because the phase space of these fields are, well, huge. Each location a degree of freedom. And the mathematicians have a few problems with doing that. But fortunately, we are physicists, so we are not too afraid and have done such things for quite a while. And the simplest way to do is we pixelize the space. So we introduce pixels, and at each pixel location, the field value has only the field has only one value, and here a different one, but it's the same value within a pixel. And so now we have only n degrees of freedom, and our phase space integral in this pixelized version of the field is an n-dimensional integral. N might be a large number, a million or so, but it's still a finite dimensional integral, and probability theory is well defined over finite dimensional spaces. But of course, you might argue that this is a poor representation of all the small-scale details going on in that field. And so we should request a further thing, namely that we are allowed to increase the resolution of our pixelization without that this integral changes essentially as soon we have sufficient resolution in order to resolve all the important small-scale details. So if this is possible, if we can increase the resolution further and further, and from a certain point on, the value of this average over this discretized phase space integral doesn't change anymore, then we can say, oh, we're basically in the continuous limit, because increasing the resolution further doesn't change anything. And we could pretend that we can go to an infinite resolution. In practice, we never have to do this. We just could stop at that resolution as soon as it's sufficiently high. And so we have then a representation of our fields and even probabilities over these fields. So an information field theory, I would argue, is defined over continuous space, but the calculations can be performed in sufficiently fine discretized spaces. And when we apply this on a computer, we will always work, of course, with a discretized version of that. And by this trick to map our inference problem to a statistical field theory language, we actually have directly a dictionary how to translate between inference language and statistical field theory. And here you see the beginning of such a dictionary. You saw the negative Hamiltonian is a logarithm of the joint probability distribution. What is called evidence in Bayesian reasoning is a partition function, and so on and so forth. Okay, so how does this work in practice? And let me walk you through the simplest case one can deal with this information field theory. The simplest case is that of a free theory. And it emerges in case we are looking at a Gaussian signal, like the cosmic microwave background, of which we believe to a high precision is drawn from a Gaussian process, observed by an instrument with linear response, which is subject to Gaussian noise, linear and Gaussian noise. So the probability distribution of our signal should then be a Gaussian, which I write in this form with a normalization here, an E function to minus a quadratic form in the small s value. And here's a big matrix. This matrix is the two-point correlation function of the field, averaged over all of field realization in our a priori knowledge. And this is very important because in this matrix, I encode the information. If I know the field here, what do I know about the field at a different location? And this will be important when we have only sparse measurement at certain locations and want to make statements about the field value in between. The only way to go forward there is to exploit these correlations because we haven't measured in between. So if we can't use some continuity in correlation, we can't make a statement. But if we have a correlation function, then we make maybe some uncertain, but some statement. And then a technical detail, we have here a scalar product, and scalar products are defined as in quantum mechanics by the integration over the space, and these two functions you multiply with this other. But if you don't like this, you can always think this is a sum over a finite number of pixels, and then every equation is also valid. So we have now specified our prior. Now comes the measurement. The measurement, let us assume it's linear, so the data is some response operator applied to the signal plus some noise. This response operator maps a continuous field into a finite number of numbers. It's a data vector. And some noise is added. And we assume the noise to be Gaussian as well with a noun-noise covariance matrix. Okay? Now we can build our joint probability of signal and data by multiplying this probability, which is a Gaussian, with this probability, which is also Gaussian. Both involve S. So these are both Gaussians in S. And we can use the fact that Gauss times Gauss gives Gauss, normalize, and get our so-called posterior distribution of the signal given the data, which is again a Gaussian. Now with a shifted mean, the mean is not centered on 0 anymore, but around some m. And the variance is not the original signal covariance, but is this d. The posterior mean can be calculated as applying the same d as up here to some j, and this j I call information source, because it contains the data, which is the source of all the information we get. And what it is the data inversely noise weighted and back projected into the signal space. And since I see Brian here, this is a dirty map in radio interferometry with natural weighting. Okay? So, and this dirty map has then further processed and it has to be processed by applying this D. And this D I call information propagator for a reason which gets clear in a second. This D knows about the signal covariance in order to extrapolate into the regions where we haven't measured, and it knows about how the measurement was taken, and combines all this into something non-trivial by this matrix inversion. Okay, that's the free theory of information field theory. And this is actually not new. It's known for more than 60 years because this is a generalized Wiener filter. So whenever you have a Gaussian signal measured with a linear instrument and Gaussian noise, and you want to know what is a posterior mean, the Wiener filter is calculating this for you. But many instruments are non-linear or have non-Gaussian noise, or the signal is non-Gaussian, or the noise depends on the signal. In this case, the situation gets a bit more complicated. Then we get an interacting theory, meaning that the Hamiltonian in this case was only quadratic in S, and now we have higher order terms in our Hamiltonian, which make the mathematics a bit nasty. Fortunately, the particle physicists have developed a quite extensive field theoretical toolbox to treat such nasty problems. So they have developed Feynman diagrams, renormalization calculations, resummation techniques, effective action approaches, and so on. And some of these approaches are also known in the inference under the term maximum entropy or variational base, which is the same as mean field theory. So we can use all these tricks developed by quantum field theoreticians in order to develop inference algorithms.
So when you do like the pixelization,
A pixelization, yeah?
in terms of field theory, I think it corresponds to like putting a hard cutoff.
Yes.
And sometimes there's things like the result may depend on like the actual cutoff. But you can get rid of those things by doing like more sophisticated like renormalization.
Yeah. So as long as you stay with the Gaussian field, then this cutoff is not a problem. As soon you have non-Gaussian responses or transformation, then you actually have to be careful when you specify the parameters of your Hamiltonian for which discretization you have used them. And basically the same renormalization and mass scale dependence as in quantum field theory appear also here. Yeah. But for this talk, I want to sweep this under the carpet. Okay. Okay. Interacting theory. The Hamiltonian is just the negative logarithm of this joint probability. And I do a Taylor expansion of it. If this Taylor expansion in S goes only up to second order, then I call this a free theory. And what I get is this generalized Wiener filter. But if I'm unlucky and have a non-Gaussian signal or so on, then I get higher interaction terms where third or fourth or higher order combination of the signal field interact, and I have some Taylor coefficients here, and I have to do sum over all degrees of freedom, so it gets really a bit messy. Fortunately, there's something like Feynman diagrams, which allows us, in case these coefficients are small in a certain sense, to expand the solution around the Gaussian solution. And here I wrote down the Taylor series for the expectation value of the field in terms of the Feynman series. This is a simplest diagram. Then here we have an interacting, and then one with a loop, and so on. And if I translate these back into formula, the dot is represented by this information source, J, and the propagator, which transports information from a measurement at one location to the location where I'm interested in, is represented by the line, and that's the reason why we call this D information propagator. So this first diagram is DJ, which is just the Wiener filter. And then I have higher order terms which involve these coefficients. And if these coefficients are small enough, then one can truncate this series and has directly an algorithm which calculates the posterior mean with a certain accuracy. This is one technique. There are others. But maybe that's the one which is graphically most appealing. So again, here's a Wiener filter. I have some measurement which tell me about some location, and the information is propagated. In case I have this diagram, because this 3 vertex was non-zero, then I combine the information from 2 locations at a third locations and in a multiplicative way, and propagate the result to the location where I ask my question. And then there's things like loop diagrams, which do not depend necessarily on the data. They do some corrections to, well, renormalization effects, as you mentioned. And for example, one estimator for what we call a non-Gaussianity parameter in CMB science is drawn here in its diagrammatic form. So let's assume that the gravitational potential in the early universe is a Gaussian random field. Well, there was a Gaussian random field from which the gravitational potential emerged in a linear and a nonlinear fashion, and we want to know if this parameter f is 0 or different. And then if you calculate these diagrams, then this is an estimator for this f. And actually, these top 4 diagrams were developed in a period over 7 years in a series of papers. And for me, writing this down was basically an afternoon of work. So you can see you can derive algorithms which also have some aesthetical appealing if you draw them. The important thing is, if you want to calculate this in practice, we have to operate with the Wiener filter, because each line is basically applying this information propagator, which is the essential part of the Wiener filter. So let's look for a few minutes to an instructive use case of the Wiener filter, which is non-trivial. Imagine we want to measure the electron density within our galaxy in the Milky Way. Yeah? So here I drew a mock electron density field from some power spectrum, and we want to measure that. And the way we measure that is using pulsars, which send us pulses which disperse on the way to us. And by analyzing the pulsars, we get the line of sight integral of the electron density between the Earth and the pulsar. So for all these line of sights, we know basically how many electrons are on this line of sight by our measurement, but we don't know where they are. So let's see what the Wiener filter does with such data. The Wiener filter says, okay, the first thing is I have to calculate this information source. I take the data, inversely noise weight it, and then back project it into the signal space, so into this domain here. Back projected to all the locations where it could have contributed. So doing this produces this image. This adjusts the line of sights with the measurement signal projected back. And you can't see very much, because we haven't applied the information propagator, which propagates the information from all this line of sight into the environment, and also makes a different thing if we have 2 line of sights which are basically the same, but one is a bit longer than the other, which allows us to see if there are electrons down here or not. So if you apply this D to this J, we get this image. That's a Wiener filter reconstruction. And if you compare it to the original signal, we see that the large-scale features are there. The small-scale features are, of course, not reconstructed because we had too few line of sights. And yeah.
That's a Gaussian signal to begin with?
Yes, this is a Gaussian signal to begin with. So it's very simple. Just to show that.
So could you describe the prior power spectrum?
So we informed the Wiener filter about the power spectrum we used to generate the signal. So we were cheating in all respect.
Well, I know you were cheating. I'm just questioning exactly how you cheated. I mean, what was the assumption?
The assumption was that it was some power spectrum, which I had here, and that we know that it is this power spectrum.
Oh, so that's the input power spectrum.
Yeah. This was the power spectrum used to generate this field, and this was the power spectrum about which we informed the filter. Okay? So we were simplifying our life a lot. In practice, one has to measure this power spectrum from the same data which measures the signal one reconstruct, which makes the problem much harder. But we can do that, even in this tomography case. And the result is shown here. So this is, from real data, a three-dimensional reconstruction of the electron density of the Milky Way. You see the plane of the Milky Way, different planes going up. I stop this in the middle, in the mid-plane of the Milky Way. The Earth is here. Only 68 pulsars were involved in this reconstruction, so that's why this picture doesn't look too impressive. The Gum Nebula is sitting here. You can see the local bubble. You might see the next spiral arm and maybe something in the direction of the galactic center, but I wouldn't bet too much on that.
So the y-axis is galactic latitude? No.
Oh, this is in the galactic plane.
In the galactic.
This is, yeah. So the movie was going from below, higher and higher, different slices of the galaxy.
Why only 68 pulsars response with distances?
Because we have only distances for 68 pulsars. We would need many more. And also in this movie, in this, we were cheating a little bit. But I'm not talking about that. That's why you haven't seen a paper out of that. But in principle, this should just illustrate, in principle, it's possible. And the power spectrum was inferred from the data itself, which is, of course, not a high precision inference, but gives us some rough feeling.
But this is the mean field.
Yeah.
And whenever we show Wiener filters, what is fundamental to show is the some example fluctuations to show you in terms of where the believability is higher and where it's lower.
Okay. And in order to show such a case, let me turn to another example. I don't have it for the electron density. These are 41,000 locations on the sky where we have a Faraday rotation measurement. Exagalactic radio source sending us polarized emission, which gets rotated by the Faraday effect, mainly in the Milky Way. And data is sparse, and we want to make a continuous map out of that. People have done that, used this data. This is the result of a top hat median filter with 7 degrees diameter, done by Taylor et al., the people also who built this catalog. But some of us thought we can do better, and one of the person was Niels. He's here. So this was part of his PhD. This was a reconstruction of the galactic Faraday rotation from this data, assuming that it can be described as the Faraday rotation as a Gaussian random field, times some galactic profile, which we have to infer as well, with an unknown power spectrum, and even with unknown noise values, because noise variances, because well, we had some indications from the observers, but we found that, well, it's well known in the field that many of these error bars are incorrect, so we had even to add a nuisance parameter, or Niels had to add a nuisance parameter concerning the noise. And we get a nice continuous map. It's not as good as down here in the southern region where we have only a small number of sources, but in the galactic plane it's quite detailed, and some of these structures up here are also seen in X-ray and gamma ray and in other wavebands. There's an interesting thing about this. Brian Gensler and others took these exagalactic measurements, subtracted this map, and because whatever is not in this map, one would assume should be exagalactic. And then they found out that in the residuals, there is a latitude-dependent trend in it. And I said, no, this can't be. This is a perfect map. This is good data. The difference can't show a trend. But then Brian showed me a plot that this is the case, and so I lost a bet to Brian about a bottle of wine, which I wanted to give him today. So I selected a very nice bottle of wine, but then unfortunately I was informed that at this institute alcohol is not allowed, so it had to be converted into some grape juice. But if you wait long enough, it might turn into a good wine or vinegar.
Thank you. I won.
And the reason why I was wrong, and this is still a good map of the Faraday skies, is the uncertainty. And so here's the uncertainty map for the Faraday rotation map. And the uncertainty is much, much larger than the galactic plane. And this filtered map tries to suppress the noise as much as possible and leave the noise in the residuals between the data and the continuous map. And therefore, the variance of the residuals were larger in the areas where the noise of the reconstruction or the uncertainty of the reconstruction is larger. Okay? Yeah. I want to show you another example where we apply this theory. And for that, I have to open a big bracket, because now I put in a different talk I gave last December at the Planck meeting about the decomposed Fermi gamma ray sky and its relation to the Planck microwave sky. The work was done by my PhD student Marco Selig, but Niels was also involved. What you see here, unfortunately you can't see it, maybe you can switch off the light for a second. What you see here is a Fermi gamma ray sky, color-coded, the individual photons color-coded, hard photons in blue, soft photons in red, in an energy interval between a GeV and 300 GeV. And Marco Selig developed an algorithm to denoise, deconvolve, and decompose photon observations, which is applied to this data. This algorithm was developed with an information field theory, and we had to face a few challenges. Namely, that if you look at the sky, there are two signal fields, a diffuse emission and point sources, which are superimposed on the sky. The sky is observed with the instrument, and so we get photon counts. And while these photon counts have Poisson statistics. And from that data, which has Poisson statistics, convolution in it, we want to reconstruct the diffuse and the point-like component. The problem is at each location, there could be a point source or diffuse emission or both, but we have only one value. So the miracle we have to do is to turn one number into two. And the only way to do this miracle is to put in more information. And the information in this case is that we try to specify what we understand with diffuse and point source. And so for the diffuse, we say, okay, it is drawn by a log normal model, so some Gaussian random field exponentiated, so that it varies on a logarithmic scale. And this Gaussian random field has, of course, a power spectrum. And this power spectrum itself is unknown. So we have to put a prior on the process, on the stochastical process producing this smooth field. And we assumed further that the spectrum is not, as a function of wave mode, is not changing too rapidly, that there are no spikes in the power spectrum of the log normal field. And this leads to three model parameters in order to tune with a hyperprior fixing our power spectrum. Our point-like field is in every location there could be a point source. Most of them are so faint that we don't see them, and only some stick out, and point sources are not correlated. So the only thing we have to specify what is a brightness distribution, and there we assume some power law with a cutoff, and which gives us two more parameters to fiddle around in order to specify our prior. So we have 5 parameters to fiddle around, and for most of them, they're very natural choices, leaving maybe 1 or 2 parameters to tune the algorithm. That is D3PO, and that's how it works. In one dimension, you see here the instrument response convolved signal, so the combination of the continuous signal and the point sources. And here you see the counts, 1 count, 2 counts, 3, and so on as a function of location. And from these counts, we want to reconstruct the original field. And here you see the result D3PO delivers as a function of the coordinates. So you get back a continuous field, and you get point sources at various locations. Not all of them are found because they are too much buried in the noise. And we have coded this in a way that it runs in 1 dimension as well in 2 or 3 dimension. So here's the same code run on a 2-dimensional problem. The input data, point sources, diffuse emission, and here is a reconstructed diffuse photon flux, I believe. Yeah, and here's the point sources identified. So this algorithm derived under information field theory was then applied to the gamma ray photons from the Fermi satellite. Here are all the photons again. And the result of the reconstruction are 2 maps, one with a diffuse flux and one with the point sources. If we add them back and and calculate the instrument response and calculate the difference to the original data, we get the residuals. And if you compare this map to a similar map given by the Fermi collaboration for their sky model, you see that our residuals are much, much smaller. Their way of generating diffuse maps is by using templates. So they used known tracer of different, H1, different emitters, and their spatial templates, and made a linear combination out of them in order to construct the diffuse flux map by fixing these parameters. And so their model is not as flexible to follow what the photons want. And therefore, the relative difference between our map and the Fermi map, so our map minus the Fermi map, or the other way around, divided by this map, can be up to 50%. So our map is quite different to the Fermi map. Of course, the large-scale features are all the same, and the main point sources are the same, but there are significant differences. We made this game not only with all the photons. We did this actually in energy bands. So here's a 1 GeV band, the 2 GeV band, and so on, up to 200 GeV. Here's the data. Here our diffuse reconstruction. For each of those, we also reconstruct the power spectrum. So here you see the power spectrum of the different energy bands, and they look quite similar up to a location where the sparsity of the photons doesn't allow us to resolve details. So that's why we have different cutoffs for the different energy bands. And we can combine all these maps into a single image by color coding it, putting red to the low energy and blue to the high energy. If you do that, that's what we get for the data. You see mostly the galactic plane, which is bright due to various effects, but you don't see so much above and below. In order to see a bit more what is going on at higher latitude, we change the brightness scale, but not the color scale. So now we change to logarithmic brightness instead of linear brightness, and then the same data looks like this. Okay, you see some known features, like for example, the Fermi bubbles are already visible here in the data. So now to this data, we apply the D3PO algorithm, which denoises, deconvolves, and decomposes. Let me go through it again. So that's if there would be a separate denoising step, that's what it would do. Taking out the shot noise. Then the deconvolution step does most at low energies. You see these red spots, which are due to the bad point spread function at low energies. So these become tiny red points due to the deconvolution. And finally, the 2 fields, the point source field and the diffuse fields, are separated. And here we have the diffuse emission of the Milky Way. And here we have the point sources. And by the fact that there's this red background, you see that there's a point source at each location. So, but most of them are so faint that they don't contribute much. There was a question?
So the step is that you assume that the diffuse distribution had a logarithmic distribution, which you began with some assumption on the power spectrum, and then you iterate on it until it reached convergence?
Yes.
And how long is it, how many iterations do you require to get convergence? And is it much different than what you began with? How robust is it?
So our initial power spectrum we put in, we typically put a high one because it's better to let the power spectrum fall than to go up. And it takes quite some time, maybe 100 iterations, and making these maps takes a few weeks or so. So it's nothing which you can do in an afternoon. But for a problem like this, we have the time. So.
What often happens with these things is that convergence is fast on some scales, slow on other scales.
Yes.
Long wavelength.
Yeah, this is indeed a problem. So our fix for that is that we start with a large scale reconstruction, and once this is converged, we go to smaller and smaller scales. Yeah. So the numerics of this is a bit delicate. Yeah. But that's how it is. These are very high dimensional, non-convex optimization problems, and there are no known perfect recipes how to deal with them. And well, we try this and that, and that's what we got.
You sort of, I've seen in the past, use the multi-grid approach.
That's something we want to do as well, and have started to work in that direction. But it was not used here. Yeah. Okay, so the point sources, let's do a little bit astrophysics with the results because they're so nice. So the point sources can be put into a catalog. So we've put out a catalog of 3,000 D3PO Fermi point source candidates because we didn't verify them. We cross-matched them with a third Fermi catalog and have nearly 2,000 in common. And if you just compare the statistics, so here are our fluxes, and that's the Fermi fluxes, then for the bright sources, they are quite similar. But since our diffuse background model differs, there's also substantial differences. And we have to see in the end who was right and who was wrong. But more fun, I would argue, is the diffuse gamma ray sky. So here you can clearly see by eye different physical processes in operation. You see that the Fermi bubbles have a different spectrum than the galactic plane, or these cloud regions in the galactic anticenter. You see the spectrum of the gamma rays from there encoded in the colors. We can, of course, also measure the spectra there, since we have 9 energy bands. So we took a spectra here in the southern bubble, which is far away from the disk. We took some from the disk, and we took some from this cloud complex over there. And here are the energy spectra. So the cloud-like is this one, and it has a bump up here, which looks a little bit like the pion bump you get if cosmic ray protons interact with other protons, and then neutral pions are created, which decay into pairs of gamma rays. And this has a peak around the rest mass of the pions, which at a GeV leads to this turnover. And that's also physically very plausible. That's in these dense clouds we have interaction of cosmic rays with thermal gas and with dust. Whereas in the bubble region, it's more like a power law. Well, we shouldn't trust in the last spin. There are some problems here. It looks more like a power law, and so a plausible interpretation is that these are relativistic electrons, because there are not so many targets up there, interacting with the photon fields, cosmic wave background, starlight, and so on, and producing inverse Compton radiation. If we now look into the disk, here's the disk spectrum. This spectrum looks intermediate between these two, And indeed, a linear combination of these two can give a quite reasonable fit to it. So we said, okay, maybe all the gamma ray radiation, the diffuse gamma ray radiation of our Milky Way, might be explained largely by these two spectral templates, which are mostly due to pion decay and mostly due to inverse Compton. Let's try this. So this is a mix of hadronic and leptonic everywhere. So let's take the diffuse flux map and point by point decompose it into only two components. The one I've shown you, one with a spectrum like here, the other with a spectrum like there. And the answer is, that's what you get. That's the cloud-like component, and that's the bubble-like component, which of course has the bubbles, but also a lot of other bubble-like emission, and probably inverse Compton emission everywhere in the galactic plane. If I combine them back in a linear combination, that's what I get. And 90% of the photons of the flux in here is also in this combined map. So the claim is that with two components, we can explain 90% of the gamma ray emission, diffuse gamma ray emission of the galaxy. And this is probably the dense interstellar medium where there are a lot of targets for the cosmic ray protons to detect. And this is probably the dilute interstellar medium, the hot interstellar medium, where there are not so many targets, so we don't see a pion bump, but we have inverse Compton emission because this is large in volume. Let's look first at the cloud-like component, here again in a different color scale. The reason why we have chosen this color scale is because it's the same color scale also the Planck collaboration uses in order to make a dust map. Here's a Planck dust map. And you see some similarities between these two. Here in the middle, it's a bit distorted because the fit wasn't so perfect due to the Fermi bubbles. But nevertheless, if you look at these features here, they are also in the Planck map, a dust map. And if I block this distorted area and blink between these two maps, you see a lot of similarity. Look at this arc up here, or the structures down here. So one of them is probably cosmic ray protons interacting with gas, and the other one, and the other one is infrared and microwave emission from dust grains heated up by starlight. Morphologically, very similar. We can compare these two maps by taking the ratio of one of the other as a function of latitude, and we find that the dust profile is more narrow than the gamma ray profile. And this can be interpreted as that the cosmic ray targets, which is the gas, is at higher latitudes than the starlight targets, which is the dust. Or that there is some evidence for gravitational stratification of the different components of the interstellar medium from comparing these two maps. Okay, let's compare the bubble-like and the dust-like profiles. And by eye, you can see that this stuff wants to get out. And the profile of the bubble-like is much wider, and here we excluded the Fermi bubbles, than the dust-like. So the interpretation is that this is just the hot phase of the interstellar medium which wants to break out of the disk. And the Fermi bubbles are just a normal hot interstellar medium produced by very active supernova explosions in the galactic center, which then lead to these outflows. Nothing special. Again, here the Fermi bubbles, the photon spectral index is 2.4, which is no problem for this Compton. In Planck, we have observed a 30 gigahertz haze with a similar spectral index. And this is interpreted as synchrotron emission, probably coming from the same electrons. But also we can look at the morphology of this emission here in the disk, these bright spots. If this is really hot interstellar medium, which is traced here by relativistic electrons, upscattering photons, then other tracers of the hot interstellar medium, for example, free emission, should show it as well. So here's a low-frequency Planck map, which among synchrotron emission also contains free emission. And if I blink these two maps, you see that there are a lot of morphological similarities. this interpretation might be correct. Okay, I could now go through all the results of this Fermi analysis. However, this was an information field theory talk, so I should close the bracket and get back to the conclusion of my main talk. Signal field inference is always an ill-posed problem. We have finite data and want to determine an infinite number of degrees of freedom. We always have to use other information in order to get something reasonable. And the way to combine this information is using information theory, which leads to information field theory, which is just probabilistic reasoning on fields. We can steal techniques from quantum field theory. We exploit the spatial correlation structure of the signal. Either we know it from theory, like in CMB, or empirically. And we can deal with incomplete data, signal-dependent noise, non-linear response, and so on and so forth. And I showed you already a few applications to CMB science, radio and gamma ray astronomy, and beyond. Before I thank you, let me point out that there are some web resources. So there's a web page for information field theory where you can find publications, tools, and software. And for some reason, some slide disappeared from my talk where I wanted to show you the nifty software package which allows you to do all these things by yourself. It's a Python library which you can install in typing in one pip command on your computer, and then you have this. And one of the demos is the Wiener filter I showed you. And you can build then with this library easily different algorithms. And this library abstracts from the spaces. So you say, I want to have a two-dimensional space, and then my field is living there. And you write your algorithm. And then you change your mind and say, oh, now I want to apply it on the sphere. And all you have to do is to exchange the space. Say, instead of a two-dimensional Cartesian grid, I want to have a heel pix over the sphere. And your computer code still works and does usually sensible things. So if you're interested in these things, I highly recommend this nifty library. And if someone wants to get a hands-on, come to me and I show it on my laptop. Or check it out from the web. It's just one command to install. The D3PO code is also open source now and can be installed by typing in one command. And the data from the Fermi analysis is also freely available. So thank you for your attention.
All right, thanks, Dustin. Are there any open questions?
So the deconvolution in the D3PO, is that deconvolving a linear convolution, or can it be a nonlinear convolution of the signal that produces the data?
What do you mean with nonlinear convolution?
Say the data is
A convolution is a...
would be the luminosity of the source at some frequency.
Yeah.
The convolution, could it be a function of powers of the luminosity of the source?
So the convolution could be different at different frequencies. That's well possible. It is a linear operation in the sense you have your signal field, and if you double it, you get twice as strong the data. So in this sense, it should be linear in that specific case, yeah.
The example, it looked to me like you custom designed some algorithm to apply multiple statistic for each of these solutions, and you put a log normal in or whatever. Is there any example in which a perturbative expansion actually is useful? I mean, I can see that in principle that should work, but it looks like we're doing it.
There are two cases. One is for FNL, because FNL is a small parameter, and that's useful. Also, we also have better algorithms than the diagram I showed you. And the other is sometimes you have a very nonlinear problem, but you say, okay, let's ignore that the problem is nonlinear. Let's make the parameter small, calculate some perturbative corrections, and absorb them into the propagator and the source, and then drive the parameter up and do the renormalization calculation. So we have used Feynman diagrams in order to calculate renormalized algorithms. And they work. They work for the log normal field. The log normal Poisson problem, I derived an algorithm like that. And since I said, okay, that's great, and let's try to understand this a bit more, and I discovered that actually the solution I got was equivalent to a renormalization calculation is usually the same as minimizing an effective action or a Gibbs free energy. And the Gibbs free energy can be shown to be equivalent to what the signal inference people call an entropy. So there's a deep connections between maximum entropy techniques and signal inference and the results you get if you do renormalization calculation. But doing this renormalization calculation, Feynman diagrams are useful.
All right. Any urgent other question?
I'm misunderstanding the use of effective action. Usually you put in some kind of driver out of the equilibrium state, and then you try and do the integral with that as a variable that creates the effective action. And that's how you come up with effective potentials, etc. The problem with that is that integration, unless you do a lot of approximation, is not easy to do in Japanese theory. So I'm not quite sure why you say that's maximum entropy.
Okay.
Actually trying to do, where the gradient is.
Because I left out the detail. The detail is that when we do the approximation, we say we want to characterize our field by a mean value and the variance, and which means we characterize it by a Gaussian distribution. So we say we want to find a Gaussian distribution which has the right mean and variance, and put this template into this entropy or effective potential formula. And then we can solve these equations. Is this answering your questions? So we do an approximation, a Gaussian approximation, and try to get the mean and the variance of this Gaussian correct up to some correctly fitted to the non-Gaussian real distribution.
Maybe that needs to be discussed more upstairs. I think we've earned a cookie now. So before we go up, let me point out that we'll be taking Thorsten out for dinner tonight. So everyone's welcome. If you would like to join, just let me know. And Thorsten will be around the whole week in the virtual office, so feel free to disturb him.
Yeah.
Thanks.
Thank you.